All right, let's talk about something that's literally holding our digital world together, but you've probably never even thought about it. I'm talking about cryptographic hash functions. They're these silent workhorses, the absolute foundation of online trust. So let's dive right in.
Okay, so picture this. Your phone buzzes. New software update. You just tap install, right? We all do. But have you ever stopped to think, how do I know this is actually from the developer? How can you be sure it's the real deal and not some piece of malware that someone snuck in?
Or what about this? You log into your favorite website, it knows your password is correct, but you'd really hope they aren't just storing your password in a big, plain text file somewhere, right? Because if they get hacked, that's a disaster. So how in the world do they verify it's you without, actually storing your secret password?
Well, the answer to both of those pretty big questions is this really clever concept called a cryptographic hash function. It's this beautiful mathematical tool that solves these exact problems of trust and security, and it does it so elegantly.
So the easiest way to wrap your head around this is to think of it as a digital fingerprint generator. Seriously, you can take any piece of data, that software update, your password, a whole movie file, anything, and you feed it into this function. What comes out the other side is a unique string of letters and numbers. We call this a digest, but honestly, digital fingerprint is the perfect way to think about it.
And these digital fingerprints have a few, well, almost magical properties. First up, they're deterministic. That just means the exact same data will always produce the exact same fingerprint, no exceptions. Second, it's a one-way street. You can't take the fingerprint and work backwards to figure out what the original data was. And third, they're always a fixed size. The fingerprint for a single word is the same length as the fingerprint for an entire library of books. Kind of weird, but super important.
Okay, but here's the real kicker. The thing that makes this whole system so secure, it's called the avalanche effect. And this is the part you really got to get. If you change even one tiny thing in the original data, I'm talking one letter, one single pixel in an image, the digital fingerprint that comes out is completely, totally, wildly different. It's not just a little different, it's unrecognizable.
Just look at this. This is the avalanche effect in action. We've got two messages, and they're almost identical. The only difference is one single character. But look at their digital fingerprints. They don't look anything alike, not even close. That is what makes this so powerful.
Okay, so that's the theory. But how is this whole digital fingerprinting thing actually used? Where do we see it out in the wild, protecting us every day? Let's get into the practical stuff. Let's circle back to that first question I asked, downloading a software update. The developer needs a way to guarantee 100% that the file you're getting is the exact one they made with zero tampering. No viruses, no sneaky changes, nothing.
And here's how they do it. It's actually super simple. The software author creates a unique fingerprint for their program. When you download it, your computer generates its own fingerprint of the file. And then it just compares the two. If the fingerprints match, boom, the file is authentic. If they don't match, even by a single character, warning, something's wrong. You know it's been messed with.
And once you see this pattern, you see it everywhere. Digital signatures, they use hashes to prove a message is from who it says it's from. Blockchain and cryptocurrencies, the entire chain is just blocks of data linked together using these hashes, making it basically unchangeable. And yeah, to solve our password puzzle from earlier, websites don't store your password. They store the hash of your password. When you type it in to log in, they hash what you just typed and just check if the fingerprints match. It's genius, really.
Okay, this all sounds pretty solid, right? But how secure is it really? I mean, can't it be broken? Let's really dig in and see how tough these things are.
Yeah, let's think like a hacker for a second. How hard is it to forge one of these digital fingerprints? What would it actually take to fool this system?
The first big security wall is something called pre-image resistance. It sounds fancy, but it's just that one-way property we talked about. A detective finds a fingerprint. They can't just plug it into a machine and print out a picture of the person, right? It doesn't work that way. Same thing here. A hacker gets a password hash. It should be practically impossible for them to work backwards and figure out your actual password.
The next level of security, and this one's a biggie, is collision resistance. This just means it has to be next to impossible to find two different files that produce the exact same fingerprint. Because think about what a disaster that would be. A hacker could create a virus and then tweak it until it just so happens to have the same digital fingerprint as, say, a legitimate software update. Game over.
So how do we stop these attacks? How do we make these things resistant? Well, the math behind it all is super complex, but the answer is surprisingly simple. Length. It all comes down to the length of the fingerprint. A longer fingerprint means there are just astronomically more possible combinations. It makes it exponentially harder for an attacker to just guess their way to a match.
And you can see that evolution right here. This is basically a history of the security arms race. You've got older, shorter hashes like MD5 and SHA-1. They're considered broken now. They're just not long enough. Today, the standard is the much, much longer SHA-256 and SHA-3. The trend couldn't be clearer. Longer equals stronger.
But you know how it is, the arms race never really ends. The people who build these systems are always looking over the horizon for the next big threat. And the one that's looming largest right now? Yeah, it's quantum computers.
Now, we're not just talking about a faster version of the computer on your desk. These things work on a completely different set of rules, the rules of quantum physics. And it just so happens they're really, really good at solving some of the problems that make our current cryptography secure.
So there's this quantum trick called Grover's algorithm. And what it does basically is make that brute force search for a matching fingerprint way, way faster. As you can see here, it effectively cuts the security level of a hash in half. So a 256-bit hash, which is super strong today, against a quantum computer, well, it only feels like a 128-bit hash.
Okay, so cutting security in half sounds terrifying. But here's the crucial context. Even with that massive speed up, a quantum computer would still need to perform something like 2 to the power of 128 operations to break it. That number it's just mind-bogglingly huge. We're talking more operations than there are atoms on planet Earth. It's just not going to happen, not for the foreseeable future.
So, what are the experts saying?
The consensus is pretty clear. Because cryptographers saw this coming and we moved to these really long hashes, our current standards, things like SHA-3, are expected to be just fine. They're what we call quantum resistant, at least against these kinds of attacks.
So, when you pull it all together, what's the big takeaway? It's that these things, these cryptographic hash functions, are the silent, essential guardians of our digital lives. Every time you log in, every time you download an app, every time a crypto transaction happens, they're there in the background, making sure everything is authentic and trustworthy.
It's amazing, really. Our entire digital world is built on these fingerprints of trust. They're this incredibly elegant solution that's worked for decades. But it does make you think, doesn't it? As technology keeps racing forward, what are we going to have to invent next to keep it all secure?